As we step through each phase of the analysis of this WASP-12b observation, we will first be showing where each phase fits in the overall analysis pipeline. So let's start with the first phase, the calibration phase. In this phase, we will be taking the raw bias, dark, and flat files and creating from them a master for each. So a master bias, a master dark, and a master flat. We will then be taking the raw science images and using AstroImageJ's data processing function, we will calibrate the science images and optionally add fits fields that might be missing from the image capture software. So for example, we will be adding BJD TDB as a additional field in the fits header, as well as checking to see if other fits headers exist, such as air mass and so on. The output of this part of the pipeline we will call pipeline out files. So let's now begin with actually walking through AstroImageJ with our sample set of images to see how we can actually accomplish this phase. So in order to perform calibration of the science images using AstroImageJ, we would come to the main AstroImageJ menu and click on the icon DP for data processing. So let's double click on DP. And there are two screens that come up, the DP coordinate converter screen and the CCD data processor screen. For the moment, let's look at the CCD data processing screen. Here you see, first of all, an area where the science images are noted. Here I have in my subdirectory science images under directory WASP-12, my fit files for the science images. So you would enter the full subdirectory name for where the science images are, the extension with a wildcard for the file name, and the appropriate extension for those files. You notice that the total count that AstroImageJ picked up were 336 files, which in fact is the number of image files in the science image directory. Now, what's important to note is that the extension needs to be the correct one. Some image capture software will store images with an FTS extension, some with an FITS extension. So a good check to make sure that you have the right extension is to take a look at the counts. If, for example, by error, we had this as an FTS extension, you would see that the counts were 0. So putting it back to FIT, which is the correct extension for the science images we have in our example here, we do get 336. The next three areas have to do with where we would indicate where AstroImageJ would find the bias files, the darks, and the flats. Similarly, we would put the correct extension for the bias files, and we would see that the counts indeed are correct. Now, the next thing, however, under the bias calibration area is we would want to create a master. So we would enable the line indicating that we do want to create a master bias. Again, let's put that master bias in the same directory as the bias files themselves. Let's give it an arbitrary name, mbias.fit. You see currently there's no such file in that subdirectory because AstroImageJ has not yet created such a file. We are not only enabling the bias files, but I should point out also, going back to the science images, we want to make sure that we're enabling that box as well, because we do want the science images to be calibrated with the bias, dark, and flats, as we'll see in a minute. We're going to select either average or median combined here for combining the biases into a master. For the dark subtraction, we're going to, again, indicate what subdirectory the dark files are in, the appropriate file extension, confirming that the counts are correct. Similarly, we'll create a master dark file in the same subdirectory. And here we're indicating that what we want to do is to scale the exposure times of the darks in order to apply them to the flats, because the flat exposure times are typically on the order of just a few seconds, whereas the science images are on the order of many seconds. What we've done here and what AstroImageJ allows us to do is to create one set of darks at the exposure time of the science images, in this case 45 seconds, but to go ahead and automatically scale those darks, those 45-second darks, to the appropriate exposure time as if darks were taken for flats, because it is important that darks also be applied to flats as well as to the science images. So the scale allows us to scale the 45-second dark master to the 3-second flats. That way we don't have to create separate darks for our flats. Debiasing means that we're also going to apply bias correction to the dark master. Finally, with the flat master creation, we'll do similar to what we did with the darks and the biases, namely the appropriate subdirectory, the appropriate file extension, confirm that the counts are correct, indicate what file name we want to give to the master flat. And in this case, we're going to not only enable that the master flat be created, but we're going to remove any gradients that might exist. So these fields allow us to indicate where we're going to find the science images, where we're going to find the different calibration files, whether we're going to actually build masters from each of the different calibration groups, and whether we're going to enable that they be applied to the science images. So having done that, the next step is to see what parts of the FITS headers we may need to include that currently are not there. Now, if you recall, when we brought up one of our sample science images and we used the image display edit command with the FITS header option to bring up the different FITS headers, we saw that for the images, as far as this example is concerned, we had a pretty good set of FITS headers. However, one that was missing that we do need to include for our analysis of exoplanets is BJD TDB as a time base. The time base that would be typically in FITS headers are just based on Julian date and typically UTC time. So what we want to do as part of this calibration phase, in addition to calibrating the science images, is also to update the FITS headers with some values that might not currently exist. If our FITS headers, for example, did not include air mass, or if they did not include such things as the BJD TDB, then we'd want to use this FITS header update facility for doing that. So let's go ahead and see how we can include in the FITS header BJD TDB for this sample set. If we click on this little toolbar here, what comes up is different options for setting FITS headers that might not currently be there. Many of these FITS headers that we want to possibly add are generally a function of two things: the location of the target, namely the right ascension and declination, and the latitude and longitude where the observation took place. So for example, BJD TDB, if we wanted to include that as a new item in the FITS header, that's a function of both the location of the target as well as where the observation took place. What these terms in these boxes mean is that AstroImageJ is going to look for this particular keyword for object RA, object DEC, and for site long, lat, and site long to pull out the values from the FITS headers, to use those to compute a new FITS header item, BJD TDB. Here, by the way, we're including all of these extraneous other FITS header items, including one that's already there, namely air mass. It's okay to leave these defaults the way they are. If something like air mass is already in your FITS header, AstroImageJ would just overwrite it. But the important one to make sure that is enabled is BJD TDB and air mass if it's not already enabled. Now, the other thing to note, if you recall, when we were looking at the FITS header, we said that the particular image capture software for these test images had longitude as a positive number when in fact it should have been negative. So here we have an option to negate our site long value in the FITS header to indeed make it a negative, if you recall, 76 degrees, which is the appropriate number for our value for the longitude of this observation. So these checkboxes at the bottom indicate what we want to add or replace in the FITS header. We're just going to keep them all enabled, even though the one we're most interested in is BJD TDB. And the top ones indicate what AstroImageJ is going to look for in the FITS header for keywords in order to use as computation for things like BJD, TDB, or air mass. Now, there's a couple of ways of entering the important information that's needed. We said that in our FITS headers, some of the information for the object RA and DEC and the observation lat long are already there. So an easy way to indicate the target source rather than a manual entry, as we'll see that option in a minute, is just to simply say that let's look in the FITS header for the RA and DEC, and for the location, look in the FITS header for latitude and longitude. So doing this type of option, we don't have to manually put in the target coordinate source or the observatory location source, since AstroImageJ will just use the keywords for each of these two, and in this example, AstroImageJ will find those keywords and pull out the values to compute what we want to enable as a new value, in this case, BJD TDB. Now, what if we didn't have in our FITS header conveniently object DEC, object RA, or site lat and site long? Well, let's look at another option for how we can enter that information. Here we would select the coordinate converter manual entry for the target coordinate source and the coordinate converter manual entry for the observatory location source. And that's the screen that we had hidden previously. On this screen, the DP coordinate converter, the values we would then enter manually would be the appropriate longitude, as I've already done here, the appropriate latitude, and the altitude of our observing location. This observation was done at sea level, so it's an altitude of 0. And you'll notice it's minus 76 degrees, longitude, plus 38 degrees, so on, latitude. So these values would be entered for the manual entry option, and also the correct coordinates for the object would also have to be entered. All right, so let's go ahead and do that. So for this particular object, namely WASP 12, the RA is 06, 30, 32.79 seconds, and the deck is at plus 29, 40, 20.4. So if we didn't have in the FITS headers site long, site lat, object RA, and object deck, we would use this manual entry approach for putting that information in. Okay, now let's go back to our data processing screen. Well, we had in our FITS headers those particular keywords. So let's go back to the easier process, which is picking up from the FITS header the target information and picking up the latitude and longitude. And having done that, we're now ready to execute the calibration. So let's just, before we do that, review what we did. We put in the subdirectory for the science images, made sure that the counts are correct, put in the subdirectory information for the bias files as well as where we want the master, made sure that the counts are correct, did the same for the darks, the flats. We indicated we want to scale the darks, exposure time, so that we can use those darks for as darks for the flats. And we indicated that we want to remove the gradient for the flats. We're going to pick up from the FITS header the keywords that will tell us what the coordinates are for the target, as well as what our latitude and longitude are for the observing location. Finally, we want to go ahead and enable AstroImageJ to do the calibration, use the 32-bit floating point output option. We're going to have AstroImageJ put the output files with a suffix of _out in a subdirectory called pipeline out. So we are now ready to execute. When we hit start, AstroImageJ will first go through, create the masters for the biases, for the darks, for the flats. It'll do the appropriate scaling for the darks, and then it will go through each science image and do the calibration for each science image, as well as to include in each science image any FITS header updates. So let's go ahead and start that process, and we will then allow for you to see the masters being created, some of the images being calibrated, and then we'll pick up after the calibration is done. So let's go ahead and start. And what we see happening is that the flats are being created, and now the images, each image is now being correctly calibrated. Okay, our calibration has now been completed of all of our images. And let's take a look at the log file that was created. And as you see here, if we take a sample image, for example, this particular image, we see that there has been an update of various parts of the FITS header, including the BJD TDB time. By the way, it also gives what the correction is from BJD with respect to the original JD. You can see it is quite a bit, in this case 9 minutes, and this is the importance of doing our science using BJD TDB time. And we see, in fact, that the image has been bias corrected, dark corrected, and flat corrected, and then saved. And in fact, it's saved to the pipeline out directory and has an extension or has a suffix of underscore out. Now, it's always best actually to save the log file just for reference. So we're going to save it in the AIJ analysis directory. This is where we're saving things like our worksheet, our sample image that we saved earlier. So let's now save our log file just for future reference if we ever want to confirm that the calibration was done correctly. Okay, now let's take one of the images. This is the last image, 336. Let's take a look now at the FITS header. And we see the FITS header as it was before, but notice that BJD TDB has now been added as other various items that we enabled in the FITS header option when we did our calibration. So that confirms that the FITS header was indeed updated correctly. We said that we want to put these files in a subdirectory called pipeline out. So let's take a look at that directory and see if in fact it was correct, to make sure that it was correctly created. And so we'll go to our WASP-12 directory under Science Image. We indeed do see that pipeline out subdirectory, and we see that there are 336 new images with a suffix of underscore out. These are our calibrated images, and they include the FITS header updates. So that completes the calibration phase. And let's move on now to the next phase of the analysis.